Hello, for this video I wanted to do something a little bit different, and that's been made possible by the very generous support from my Patreons, or Patreons depending on where you're from. For a while I've wanted to tackle embedded systems as a topic, but I've looked for a suitable entry point that's simple enough to make into a nice video, but also lays the foundations for future video work. So let's get to it. Let's make and program a robotic arm. The aim of this video is to control a robot arm wirelessly via my computer. Here I've got my computer, and on the screen I want to have some sliders which allow me to set the joint positions of the robot's movable parts. On my computer I have a USB port, and into that I have a Bluetooth dongle. The Bluetooth dongle is going to transmit to a Bluetooth receiver. This receiver is going to then communicate with a microcontroller, micro C. In this case, it's an Mbed LPC 1768. And it's going to do that communication via what's known as a UART. And I will go through all of these terms as part of this video. The robot arm consists of 6 degrees of freedom, so that means it's got 6 movable components. These are known as servos. And the servos require a pulse width modulation signal, PWM, from the microcontroller to set their positions. So from the microcontroller, we're going to have 6 lots of PWM. We also need to think about power. We're going to power my system from a small supply connected into the mains, which is going to convert it to 6 volts. I then want to power my microcontroller by this 6 volts, but then I also want to power all of my servos by the same 6 volts. I'm going to use the Pixel game engine to draw some sliders on the screen. And I want to communicate with the Bluetooth dongle via a virtual COM port. And so the ultimate aim is that when we move a slider, we see a joint move in real time. This is the robot arm I intend to build. It's the DIY More ROT3U 6 degrees of freedom aluminium robot arm. With a claw, and this specific purchase from Amazon you can upgrade to also include the 6 servos, and I did just that, so thank you to my Patreons for funding this project. But there is no doubt it is the cheapest and nastiest robot arm on Amazon. But I think that's okay, because if we can get this to work and get it to work well, then it just goes to show you don't have to pay a fortune for some really cool stuff. The microcontroller I'm going to use is the Mbed LPC 1768. And this is a really nice microcontroller. I know a lot of you will be familiar with things like Arduino. I don't tend to use those very much. I prefer using this instead, mainly because it's also quite applicable to use in industry. I like the fact that it's so small, and it's so modular, and it's so easy to program, and we'll see just how easy to program it is later on. They're not the cheapest microcontroller modules available. However, it is entirely open source, both from a firmware and hardware perspective. And it has lots of ready-to-go peripherals. Just simple and easy to use. It also has a form factor which makes it very easy to plug into prototyping board. And a quick look at some of the specifications here. It's an ARM Cortex-M3, which is a lower spec ARM processor, but it's a tremendously capable processor. It can clock at about 96 MHz, it's got 32K of RAM and 512K of flash. It's got a whole bunch of I/O for us to exploit, but the bits I love about it the most are these. Programming is drag and drop. It pops up like a flash drive and you just drag the programmed file onto it. Very nice. And all of the coding can be done via the browser. And you might be thinking, oh dear me, that sounds dreadful. Actually, it's not that bad an experience at all. It's quite a sophisticated web interface. You can use offline tools if you want to, but that does require a bit of setting up. I like Mbeds. I've been using them for quite a number of years, even in industry. As we can see, it's quite a small device. So it measures here about 53mm by 25mm, and it's designed to fit into standard 2.54mm pitch headers. Now on the back here you can see there's all sorts of things going on, and this is what makes it easy to use. This is the user interface circuitry that allows you to just plug it into your computer and program it quite simply. But on the top is where the real stuff happens. And there's not that many features really. We have a big button in the middle. This is to reset the module. This is the ARM Cortex-M3 processor itself, and we have 4 little LEDs which are under user control. The other 2 big components on here are just power regulation, because we can provide power to this via the pins or via the USB. And there is an advantage to being able to power it by the pins. So up here we've got ground and voltage in, but because that accepts a voltage range between 4.5 to 14 volts, whereas from USB we just get 5. It's more convenient sometimes to just power your system from one place. Particularly in this case, because the servo motors that I'm going to use, I'm going to power those at 6 volts. They would work at 5 volts, but I don't have the current capacity from the USB hub in order to drive all of them, so I'm having to drive the servos from a separate power supply. Every time you buy an mbed, and I must have bought about 50 of them by now, you get a little card like this. So I have quite a stack of these things, but it's a really convenient thing to show you where all the pins are. So we can see we've got power pins here labelled in red, and all of the other pins are user configurable I/O in one way or another. So we've got 2 lots of SPI buses, and we've got 2 lots of UART on this side, and we've also got a UART on this side too. We'll look at UART for communicating between the computer and the controller module. We've also got some analog in pins, so there's a built-in analog to digital converter on here, and that'll accept up to 6 inputs. It's okay, it's not the fastest and it's not the most noise-free, but for most applications it's fine. And with some twiddling of the hardware at this sort of assembly level on the microcontroller, you can actually tidy that up quite a bit. There's a single analog out, implying that obviously there is a digital to analog converter on here. We've also got 2 I2C buses, they're usually quite popular. I don't like them as much as SPI, but it depends on the application. But most importantly for today, we've got 6 PWM out pins. So these are hardware configured. So the PWM is handled by the hardware, meaning we don't have to maintain that in software. There's also USB. So if you're doing USB on the go applications, these are the pins you'd use for that. And finally, there is Ethernet. And at best, it's a functional level Ethernet. It's not for any high-speed streaming. The whole device is really only clockable at 96 MHz, which doesn't sound like a lot, but it's enough to do a lot of interesting things for sure. The mbed also really conveniently provides a regulated 3.3 volts output, and we'll be using that to power the Bluetooth module. This is the Bluetooth module I'm intending to use, the DSD Tech HC05 Bluetooth Serial Pass-Through Module with wireless serial communication with button. And it says for Arduino, but it doesn't matter, it's just a Bluetooth module that gives us access to a UART. And I've chosen this because I'm literally just going to plug it straight into the breadboard and hope that it works. I have a little USB dongle on my main computer. And this is my Bluetooth module, and I chose this just because of its simplicity. It's entirely contained. So here you can see we've got the Bluetooth antenna, and we've got some interface chips to handle the radio, I guess. And on the back, it very conveniently labels what the pins are. And we're not interested in all of them. What we're interested in is VCC, which we're going to power it from. Now we're going to power it from 3.3 volts, not the recommended 3.6 volts you can see here. It's okay, it works. And we've got the TXD and RXD lines, they're the UART lines. That's where our communication is going to be happening. So the computer is going to transmit via Bluetooth to this module, and this module will convert it into 3V 3 level UART, which the mbed can understand quite naturally. The other pins, I'm not too interested in what they do. When you enter the world of embedded systems development, one of the first things you'll come across is the need to have things vary over time, in a kind of analogy type way, but all you've got is a bunch of digital pins. Well, one way to satisfy this is to use pulse width modulation, which sounds very complicated, but is in fact quite a simple thing. If I create an axis which represents time, and I take 2 points along that axis, this is more commonly known as the period, because what I'm going to assume is that we're going to have some repeating signal between these 2 points. Digital signals, of course, can only really be 0 and 1. Just to make this clear, I'm going to add in another timeline. So I've got 2 sections of time here. A digital clock is a signal that oscillates between 1 and 0. So for example, it may look something like this. The time that the clock is high is the same as the time that the clock is low, and this repeats. From a PWM perspective, a clock is PWM at 50%. Let's consider a PWM at 25%. Well, in this case, it's high for 25% of the period, but low for 75% of it. And it repeats. And I'm sure you've already worked out by now, but if we wanted something like 75% PWM,
It's high for 75% of the period and low for the remaining 25%. So to specify a PWM signal, we need two pieces of information. We need the period, which is this duration of time, and we need the duty cycle. There are variations of this depending on the polarity of your signals, but I'm not going to look into that today.
So let's program the microcontroller now.
Now, firstly, I must apologise. Unlike Visual Studio, I don't have as much graphical control over how the browser integrated development environment looks for Mbed, so I can't really change the font and zoom in quite as easily as I can in Visual Studio, so we'll just have to make do. But all of the source code for this will be available in the GitHub and is linkable from the description below. A blank Mbed program looks like this, and this is the environment. I've put on the dark theme so I don't blind myself, and it looks just like a C++ programming environment. I've got some files and projects down here on the left, I've got a coding window here, and I've got some output window at the bottom. And this is the skeleton stub program. You include mbed.h, which provides you with all of the tools and utilities of the board, and it gives you an int main and says, well, have at it. You can press Ctrl and B or click build from the menu up here, and it builds it and gives you the syntax error. And this is all happening in the browser. Now, since we've just been looking at PWM, I think the first thing to implement is a simple PWM exercise. So I'm just going to specify a pin called PWM out. So this is an object which will facilitate the coordination of the PWM peripherals for a specific pin. And I'm going to give that pin the name LED, LED1 actually. We're going to blink one of the LEDs on the board according to the PWM signal. And I can specify which particular piece of hardware I want when I'm constructing this pin. And on the Mbed, conveniently, it's LED1. Now, thinking back to PWM, if you remember, there are two bits of information you need to specify. The first is the period. So on my pin object, LED1, I'm going to specify the period. I'm going to set the period to be 1 second. I'm now going to specify the duty cycle by writing to that PWM pin the duty cycle as a percentage. So if I set this as 0.5, what we should expect to see is the LED blinking on and off at a half-second interval. And because I'm old-fashioned and I don't want main to exit, just in case it resets the Mbed controller, I'm just going to sit in a loop. Let's compile it. So compiling it was very simple. Well, actually, all I've done was build it, but if I click compile, it'll run through the build process and gives me a file to download, which we've just seen here. And this file is called robotarm.lpc1768.bin, which means it's a binary file, and that's the file that I'm going to drag and drop onto the Mbed when it appears like a flash drive. So I'm just going to plug the Mbed in.
I'm going to take my Mbed and I'm going to insert the USB connector directly to my computer. And we can see it's powered up the Mbed, and this LED here tells you that the Mbed has power.
The Mbed itself pops up just like a regular flash drive. So I'm going to take the binary file that's just been given to me via the Chrome browser, and I'm going to drag it onto the flash drive. And as you just saw on the camera, the LED blinked. That's telling us that the file has been flashed onto the memory of the Mbed.
I now need to press the button on the Mbed to reset it. And we can see now LED1 flashing with a 50% duty cycle on a period of 1, and that's just been done via PWM.
This does mean we can flash the other LEDs too, so I'm going to duplicate this code for the 4 LEDs on the board. But I'm going to set the duty cycles to be different, so we'll have LED2 moving at 75%, LED3 moving at 25%, and LED4 moving at, I don't know, let's pick something like 10%. Click the compile button, and straight away there's an error, of course, simply because I've not defined what the pins are. Welcome to Embedded. Let's try that again. There we go, success, and it's given me the file, so I'm going to drag that file onto the Mbed and program it. Now, you can see there's multiple files now on the Mbed. That's okay. The most recently written thing to it is the thing that flashes.
So going back to our device, I'm going to reset it by pressing the button on the top. And we can see we've now got LEDs with different duty cycles. A bit tricky to tell which one was which. But we can see that LED 4 here is a very brief pulse. That was our 10%. Whereas LED 2 was 75%. LED 1 was 50%, and we see that extinguished before the 75% one. But we see the 25% one extinguished before the 50% one. So it is working, and the periods for the PWM are all in sync.
I'm going to remove the other LEDs and just show one last thing regarding PWM. We've set the period here to be 1 second, which is actually quite slow. So I'm going to set that to be 10 milliseconds instead. And I'll introduce an additional variable, time. And in my while loop, I'm going to set the duty cycle for that particular pin to be a function of time. In fact, specifically, I'm going to set it to be sine of time. But sine will, of course, give me a value between -1 and +1. So I'm going to add 1 to that and divide the whole thing by 2. I want time to increase, so I'm just going to add a little tiny bit to it. Let's take a look.
So I've just reprogrammed the embed and I've reset it, and what we see now is a nice gently pulsing LED 1. And so PWM is really used for whenever you want something to look analogy in a digital domain. The LED is flashing on and off so quickly, and we're in control of how quickly it is flashing on and off, that we can make it look like different intensities. A very common technique on anything where you see LEDs with this sort of behaviour. Pulse width modulation is also used to regulate power efficiency in battery powered circuits, because most of the time you don't want your LED on all the time. It's quite sufficient to have it pulsing at perhaps a 50% duty cycle. To the human eye it's still just as bright, it's still a usable tool, but it's only using 50% of the power.
UART stands for Universal Asynchronous Receive Transmit. And it's a mechanism for sending and receiving data between two devices. So here I have device A, and it's going to have an RX pin and a TX pin. So it receives data from its RX pin and will transmit data to its TX pin. This could be talking to another device, let's call it B, which also has an RX pin and a TX pin, and again transmits via TX and receives via RX. If it is agreed beforehand how A and B should communicate with each other, creating a UART is very simple. We simply take RX and connect it to TX. Because this is a high-level video, I won't go into too much detail regarding the nature of the signals that are being transmitted. But this mechanism has been around for decades, and I don't think it's going anywhere anytime soon, simply because it's so easy to use. But it does require that both devices are talking the same language. So one of the properties that we'll need to set is known as the baud rate, or baud rate, depending on where you're from. And this is an agreement beforehand that specifies how many bits per second are going to be transmitted along the RX and TX lines. Once we've specified the speed at which our UART will use for transmission, we also need to specify the protocol. And a very common protocol is known as 8N1. And this tells the UART it's expecting a package of 8 bits with 1 stop bit and no parity checks. And so for transmitting a single byte across the UART, we may assume that there is a packet that looks a bit like this, where the first thing that comes along is what's known as the start bit. Then we have our 8 data bits, 1, 2, 3, 4, 5, 6, 7, and 8. Then we have our stop bit, before we go back to rest. This implies, of course, that for every 8 bits of data we want to send, or 1 byte of data, we actually send 10 bits via the UART, and the hardware will look after that for us. We don't need to do that in software, we just send the byte we're interested in and rely on the peripheral hardware to apply the start and stop bits for us. Which means we can't simply divide the baud rate by the number of bits that we want to send to give us a bytes per second value. In this particular instance, it's 10 bits per byte. So we can realistically send about 960 bytes per second. And that might seem horribly slow to those of you on ultra fiber megabit internet. There are other baud rates you can choose. There are standard baud rates, and basically they follow the old modem speeds, and there's a reason for that. But a typically high-end baud rate may look something like 115200. You can go a bit higher than this, but real world starts to play an effect on your protocol. The length of the cables need to get shorter. The nature of your circuits need to be able to handle higher speed digital signals. But also the system processing the packet at either end also needs to be much faster. Because even though here we've got a very slow clock speed compared to the microcontroller, the peripheral that's handling the UART has to have lots of individual clocks per bit in order to work out what they are. So very quickly you can see that we do need fast clocks even to handle low-speed UARTs. But thankfully for today, the mbed is going to take care of all of that for us. And in fact, an Arduino would do too. The take-home message from this is UARTs are very simple to use. And it's such a ubiquitous mechanism of communication, nearly every device you buy will have the capability to talk to something via a UART. Even that super flashy new PC you've just bought, if it's got a COM port, or it's got headers on the motherboard for a COM port, it can talk via a UART. In my robot arm application, I'm facilitating the UART via Bluetooth. The actual data transmitted via Bluetooth doesn't look really anything like the UART signal, but the Bluetooth module will reconstruct it into a UART signal that my mbed module can understand. I could, on the mbed, also use the USB interface directly. This is the one that's plugged into the computer to make it appear like a flash drive. You need to download an additional driver to do that, but it will make the USB port appear like a virtual COM port.
Now I think it's time to look at building the robotic arm. I did a full video about this, in fact it was a live stream and Q&A session, but I've condensed it now into a couple of minutes for you to have a look at.
The servo motors provided with my robot arm were the MG996R all Metal Gear servo motors. And it looks like this. It came with a load of peripherals I didn't actually need. But the servo itself is this chunky box in the middle, with a connector for power, ground and signal. The datasheet itself is dreadful, but it does have some useful information. So the operating voltage is 4.8 volts to 7.2 volts. That's okay, I'm intending to use 6 volts. But more worryingly is the running current is 500 milliamps. And it can stall at 2.5 amps. This is a problem because I've got 6 servo motors, so let's assume that's all 6 running at 500 milliamps. I need a 3 amp power supply. I don't have one, I only have a 2.5 amp supply, so I'm going to have to cross my fingers and hope that that works. Servos work using a PWM signal, and we can see here that the period of the PWM is 20 milliseconds or 50 Hz. And you'd expect the point of the signal would be a 0% duty cycle would be one extreme of the range of the servo, and a 100% duty cycle would be the other, but that's not the case. And in fact, the entire range of the servo is crushed down into a small range of the duty cycle, as alluded to by this wonderful sentence. Position 0, 1.5 millisecond pulse is middle. 90, 2 millisecond pulse is middle, is all the way to the right. Minus 90, 1 millisecond pulse is all the way to the left. I think there's been some translation going on here. However, what this is saying is that one extreme is 1 millisecond and the other extreme is 2 milliseconds, and of course the middle, the 0 position of the servo, is in between the two. So looking at our PWM signals again, let's assume they start somewhere here, or the start of the period is here. I'll draw it to here. We know that the period was 50 milliseconds. But what it tells us is that 90 degrees, so that's the servo all the way to the left, let's say, had a duty cycle where the pulse was 1 millisecond high. 0 degrees had a pulse that was 1.5 milliseconds, and the full plus 90 degrees all the way to the right was 2 milliseconds. And so the active range of our servo motors is quite narrow relative to the period. And this means we're going to need to do some maths to do this scaling for us. So let's say we have a target angle, and we'll call that 45 degrees. We're also given a duty cycle min as being 0.001, a duty max of 0.002, so the range of the duty cycle is just 1 millisecond. I also have an angle min of being minus 90, so that's to physically stop the motor from trying to damage itself, and an angle max of plus 90. So with this information we can develop the relationship between the requested angle and the requested duty cycle. And so bringing all that together, we can work out an equation to give us the duty cycle for a given angle. First, we'll normalise the angle according to its range. That's angle divided by angle max, take angle min. Given that angle can be positive and negative, this could give us a value between minus 0.5 and plus 0.5. So I'm going to offset it by 0.5 to bring it between 0 and 1. I now want to scale that to the applicable duty cycle range, which is simply duty max minus duty min. But the minimum value we can give it is duty min, so I need to offset all of that by duty minimum. Going back to a blank embed program, I'm going to start writing the code for the robot arm. I'm going to set up the hardware first, so I know I need all 6 PWM pins, labelled pin 21 through to 26, to be configured as PWM out. And in int main, the first thing I'm going to do is specify the period of the PWM for each of those pins, in this case 20 milliseconds, 50 Hz. In my main function, I'm going to want a loop that doesn't end, but this time I'm going to want to do things inside the loop. And the two main things I want to do are going to be read from the UART and write duty cycle to pins. Now I appreciate not all of these are that visible, I do apologise again. But because I see this as being the start of several robotic arm projects, I want to create a class that represents the joint, and given that this is a C++ environment, I can do just that. Now, all of my servo motors have the same physical restraints on the duty cycles regarding the PWM, so I'm going to store those as constants in this class. And you may notice if you're eagle-eyed enough that these values don't reflect what we've just seen on the datasheet. Don't forget, these are percentages of the period, not times directly. And so our period was 20 milliseconds. This is 11% of 20 milliseconds, which is about 2.2 milliseconds. And that implies that this one is indeed 3% of 20 milliseconds, which is about 0.6 milliseconds for our servos. I worked out these values by driving a servo to its extremes and just backing it off a little bit.
And I think that's a good lesson for any embedded systems design. Don't ever assume anything. If you need to do an experiment, do it.
In my joint class, I also want to store some values that represent the status of the joint. So I want a target position, where is the joint moving to, the actual position, where is the joint currently, and maybe some constraints on the minimum and maximum angles that joint can be set to. The first method I'm going to add to the class is setTarget, which takes a floating point angle in degrees and clamps it according to the joint min and joint max variables. And just for kicks, and because I like the abuse in the comments, I'm going to add a getTarget too. Next, I'm going to add a function that returns the duty cycle for a given angle, given the constraints that we have. And I showed you the maths for this a minute ago. This means I can now add a constructor. And I'm going to add a constructor that takes some default values. In this case, a minimum angle, a maximum angle, and a default position. And I'm also oddly, for now, going to add an updatePosition function. And all this is going to do for this video is take the position and set it from the target. So the user will use this joint class by setting the target, updating the position, and then calculating the duty cycle based on that position. The reason I've added this in is I think in the future I want to play with slightly more complicated trajectory planning based upon what is requested of the servo, and I'd like the microcontroller to handle that rather than the host needing to calculate it all. But since this is a very simple video, I'm just going to set the position directly to the target. In our main function, I'm now going to create an array of 6 joints. And again, via experimentation, I've determined that actually you don't want them all at 0 when the robot starts up. It starts up in a rather strange pose. Instead, I've determined that these values are quite useful for making the robot straight vertically upright. And this is where the physical dynamics of the robot are coming into play. Not everything is ideal in the real world, and so sometimes there are bits of noise and there are some offsets, particularly offsets with how I assembled the servos, because I had no realistic way of lining up where the servos were without them being powered. So once I've read the commands via the UART, I want to update all of the positions of my joints. And ultimately, I want to write those to the PWM pins.
So just exactly how are we going to communicate with our robot arm?
Given the simplicity and low speed connection of our UART, I want communication to be as simple as possible and use as few bytes as possible. But I also want it to be self-synchronizing, and that's quite an important thing when you're a hobbyist developer. Things crash, things go wrong, power supplies explode, components burn out, which means very quickly your system becomes out of sync. And as you can tell, I'm speaking from experience. There's nothing more infuriating than needing to start up your experiment or your build in a particular order in order to get things to talk. So one of the things I always try to do is make sure that communication is asynchronous in a way, so it doesn't really matter what order things are powered up in, and we should also be sure that any data that is left in any buffers anywhere isn't going to cause us any problems. We could have a sequence of bytes that represent an instruction, so perhaps we specify a joint number followed by a command followed by a value. This is a valid option, why not? So we specify we want to open the claw, and we want to, in this case, move, because we may have different move options later down in the line, and we want to specify a particular angle, all of which represented as 3 bytes. On paper, this is excellent, but in practice does suffer from some problems. Let's assume one of the bytes didn't make it across the communication, perhaps because a device has been powered up at just the wrong time. If our program on the microcontroller is always expecting 3 bytes to occur in a particular order, it will naively just assume that those bytes are correct, even if they actually started here with the move command. There's 2 scenarios here that can play out. Firstly, this 3rd byte might never be received, so the microcontroller simply stalls. Secondly, and perhaps even worse, is this move command could be interpreted as a joint number, and the value could be interpreted as whatever symbol was used to represent the move command. So suddenly we've got a situation which is quite unsafe. We could either stall the microcontroller by starving it of data, or send it commands that it interprets, but they're quite dangerous commands to actually execute. So it's worth spending the time to think about what is it that your application actually requires. So for my robot arm, I've devised a 2-byte protocol. The first byte that gets sent is going to represent the joint number, and the second byte that gets sent is going to represent the angle for the target of that joint. I'll call that joint theta. But I'm going to explore the nature of what the data in these bytes is going to represent. I know that my joint angle can only sensibly be represented by -90 to +90. I'm going to do something a bit strange here. Having a negative number means I might have to worry about sign bits and stuff like that. So I'm going to offset all of this by 128. So that really means I have an effective range of 218 as a maximum and 38 as a minimum. It's very easy for me to subtract 128 from this to get back to the original 90 to +90. But this also gives me something interesting. It means I've got space either side of this range with nothing in it. Bear with me. I've only got 6 joints in the system, and so my 0 to 6 value never overlaps with the range required by the joint theta. This means I can do a check. For every byte that comes in, I can check if the byte's value is less than 10, for example, then I know that I'm representing a joint number. But if it is greater than 10, then I know I'm representing a joint theta. This way, it doesn't matter really what byte the system receives first. Because let's say it receives a joint angle, that's going to be greater than 10. It's just going to reject it. So just by examining the data, we've come up with a way to make it robust against startup order. Yes, bytes might go missing, but ultimately it's not going to damage or stall our system. Win-win. The embed has access to the UART pins directly, but you really want to use them directly. You probably always want to run them through a buffer first, just in case your embed is doing something else and can't respond to the pins being activated for UART transfer. So I'm going to use a library that's provided by some other person in the embed community, and that's one of the brilliant things about the embed community, to handle that buffer for me. So I'm going to go to my robot arm project, import library, and go from import wizard, which pulls up this window. And in here, the library that I'm after particularly, I'm just going to type in UART and click search, and we'll see what it comes up with. And the first one that comes up is buffered serial, so I'm going to use that. I'm going to select it and click import. Now the nice thing about the embed environment is that it's basically also Git in the background, so all of the libraries and things can be updated automatically, and if somebody else in the community changes their library, I get a little notification in here that says this is ready for update. But the buffered serial library has given me 2 files, .h and .cpp. So I'm going to include the .h file at the top. And I'm going to specify a buffered serial object. I'm simply going to call it UART, and I'm going to pass to that the 2 pins I'm using for receive and transmit. I could also specify to use the USB connection too, but you need to download a driver for that. But in this case, I'm going for 2 regular pins because I'm just going to connect those pins directly to the Bluetooth module. By default, this UART is already configured with a baud rate of 9600 and an 8N1 protocol, as is the Bluetooth module, so I need to do nothing else in order to use it. So I'm going to go down to my int main and start filling in how we read from the UART. Firstly, I'm going to create a temporary variable called target joint, and I'm going to interrogate are any bytes available in the buffer for my UART, and that's done with the readable function. If there is a byte available to read, then read it please, and that's a get C. If the value of C is less than 10, then we know that that's our target joint. And if it's not less than 10, we know it represents a joint theta. So I'm going to take the joint object for the target joint we've just temporarily stored and set its angle, remembering to offset by -128 to bring it back down to a -90 to +90 range. And that's really it. That's how simple our embed program is going to be.
Obviously having a microcontroller unit and a Bluetooth module on their own is not going to do anything very useful. We need to somehow connect them together, and to do that I'm going to use prototyping breadboard. This heap of spaghetti is the breadboard that I've pre-wired ready for our arm. Now if you're not familiar with breadboard, the way that it works is all of the dots along a particular row section are connected. So these are all connected, and these are all connected, and these are all connected. But as you go down the columns, they're not connected. And this allows you to conveniently create quite complicated circuits where multiple wires are connected to single locations. Now the Bluetooth module lives over here, so I'm just going to make sure that this red wire, which is my VCC, i.e. the power for the Bluetooth module, is connected to the same row as the power in on the Bluetooth module. So I'm just going to push that in there. And the big empty space in the middle here is where the mbed is going to sit. It sits this way round, and if you remember from the card, all of the PWM, in fact I'll show the card, all of the PWM signals are along the bottom right of the module, the little pink box there if it's not visible on the camera. And they correspond to these 6 cables here. So I'm just going to make sure that that's pushed in properly and lined up. There we go. Almost. There we go. Click. So the PWM is now coming out of the module and going to this header here. This is an angled 2.54mm pitch header, or 0.1 inch to you Yanks. And I'm using this to connect to the individual servo connections. I have 6 servos, and each servo has a 3-pin connector, so here I've got 18 pins. And they correspond in order, so a repeating sequence of signal, followed by power, followed by ground. Signal, power, ground, signal, power, ground, etc., etc., all the way to the end. And I'm taking the power and ground directly from the input. So I'm going to power this board with a 6-volt power supply, and that gets split from here. So the power and the grounds go straight to the servos, and then it's also split to the mbed module. So the mbed module is being powered off 6 volts too, but it's okay with that. The module itself will provide a 3-volt 3 output for me to power the Bluetooth module, because I don't want to overpower the Bluetooth module, even though it says it is powerable by 6 volts. If I have any problems with it, perhaps I can power the Bluetooth module directly off the supply too. However, the servo supply is likely to be quite noisy and unstable, simply because it's got motors attached to it. And given that I know nothing about the quality of these servos, for the motor aficionados out there, I don't really know if they have any capacity for handling back drive. So if something, some inertial load drives the servo, I could quite easily see my power supply rails spike quite highly here. And I don't want that spike to propagate onto the Bluetooth module, because I know that that's got a maximum of 6 volts. So I'm using the regulated supply off the mbed to provide 3-volt 3, nice and isolated from the rest of the system. Here is one of the connections from the servo, and orange was signal, red is power, brown is ground. So they're just going to connect directly onto these 3 pins. Like so. So here you can see I've fastened the circuit board to the side of the robot arm, because the cables aren't quite long enough. And it's still got the USB attached to it at the moment, but I'm also now just going to switch on the power. I'll keep my head out of the way, because if you remember, the first thing that our mbed is going to do is set all the target positions to somewhere near 0 of the range for each of the servos. There we go, that's quite exciting, wasn't it?
Let's start work on making the host application. And we're back in familiar territory now. This is a Pixel Game Engine instance constructed to 400 by 400 pixels, where each pixel is 2 screen pixels wide. So it's only going to be a small window. But I've got overrides for the onUserCreate function and onUserUpdate, and I've also added one for onUserDestroy, which if you didn't know already exists, it's therefore closing up when you click the close button. And I'm not going to dwell on this too long. I really am going to be quite quick going through the code. What I want to do is present a series of sliders that control each joint. And to do that, I'm going to do a first for the channel. I'm going to use some third-party code. And this is a GUI library extension created for Pixel Game Engine by a member of the Discord community called Sleeping Bear. He also has a YouTube channel, and I'll put links to both this code and his channel in the description below. And this just allows me to quickly throw some familiar GUI components on the screen. So I'm going to add an instance of his GUI container object, and in my onUserCreate function I'm going to add 6 sliders, 1 for each of the joint. So I'm specifying the X and Y location of the slider and its length. And I'm also going to specify some default values. Now the sliders in this naive implementation go from 0 to 100 regardless. The length is the physical length on the screen. So I'm going to take the 0 to 100 and convert that to -90 to +90. So the numbers on the screen aren't accurately going to reflect what angles the joints are at. But all I'm really after here is a quick slider. In onUserUpdate, I need to tell the GUI components to update themselves. And then I'm going to clear the screen to all green in this instance, and I'm going to tell the GUI to go and draw itself. So the GUI extension is really quite nice and encapsulated like that. I don't have to do anything else. It's all going to look after itself. But it's in on user update. I also want to do some interesting things. So the first thing I want to do is get the angles from all the sliders. Well, I've got 6 sliders, so I'm going to create an array of 6 floats which represents the angles I'm interested in. And once the GUI has been updated, I'm going to iterate through all 6 sliders, get its value, and scale it to between -90 and +90. But what we're really interested in doing here is transmitting this value to our embedded system. And this is where things are going to get a bit Windowsy, I'm afraid. It is a similar process on Linux, though the syntax is a bit different. Given that I've included, as part of the Pixel Game Engine, Windows.h in this instance, I've got access to various operating system file routines. And opening a COM port is really simple. In fact, to your program, it's just going to look like a regular file stream. So I've created a handle, hcom, and set it to null pointer. And in onUserCreate, I'm going to open the COM port. Now on my system, the COM port is COM3. It will be different on different systems. You'll have to look at Device Manager or similar to work it out. But creating the COM port is actually quite simple. It's done in a single line of code. And I'll talk you through it. So it's the create file function, and you pass to it the address of the file. In this case, we want is COM3, and we tell it we want to be able to read and write to it. We're not actually going to read from it in this particular application, though if we wanted the embedded system to return information to us to display, we would want to read to it. So I'm going to leave that there. And then we specify typical file attributes and parameters. Particularly we want to open existing. We don't want it to try and create a new COM3 port. If that fails, it doesn't manage to create it, we just want to return false at this point and the application will exit. So that is it. That is all that's required to open the COM port. We just treat it like a file. Specifying the properties of a UART requires the use of the rather curious DCB structure. I'm not sure what that stands for. If you know, please enlighten me, but I'm going to assume it's something like device control buffer or device control block. But anyway, this structure contains the properties that we need to set to specify the UART. Now, the COM port will already have some properties associated with it, so I'm going to grab those using the hcom handle that we created earlier. And I'm going to overwrite the properties that I'm interested in setting for my system, namely the baud rate at 9600, the number of bits in our byte, a stop bit, and the fact there's no parity. This is the 8N1 specification. And then I'm going to rewrite this structure back out to define how that COM port should communicate. When you're done using a COM port, you probably do want to close it. This is very simple, it's just a call to the close handle function. There'll be an equivalent set to all of these functions on Linux. Writing the command via the COM port is quite simple. We've got 6 joints and we know that our protocol is going to be 2 bytes per joint. So I'll create a character buffer 12 bytes long, and I'm going to populate that buffer with all of the information required. So the first byte, or all of the even bytes including 0, are the joint number. The odd bytes, starting from 1, are the joint angle offset by 128, because remember that's what our protocol requires. So this will give us a buffer of joint number, joint angle, joint number, joint angle, joint number, joint angle, all the way for all 6 joints. I then want to periodically write this buffer to the system. Now, on-user update is going to run very, very quickly, far faster than the rate our UART can communicate at. So I want to do something on a particular tick. I don't want to do it every frame. And I like to do this by accumulating f-elapsed time. So I'll create a variable called f-accumulated-time. And only when that accumulated time variable is over a fixed amount do I want to write anything to the hardware. Remember at this point to also subtract your wait amount from accumulated time. So this gives you a very precise tick, regardless of the frame rate of the application. Writing to the device is very simple. I need a temporary value called BW, which is going to represent the number of bytes that have been successfully written by the following command, which is write file. So this is a standard file write command on Windows. It takes the handle of the COM port, it takes the buffer, how many bytes we want to write, and it will return to us how many bytes it's successfully written. Now, if I was doing this with the professionalism of somebody that works in industry, I would check to make sure that the number of bytes written is actually how many I think it is. And if it hasn't been, let's say it's only written 5 bytes out of the 12, I would then try and call this again, starting from the 5th position and working my way through the buffer. However, I'm reasonably confident it's going to successfully write all 12 bytes. This is not a particularly large demand. So in the name of clarity, I've not put in any buffer checking here. And that's fundamentally our program. We get values from sliders that are going to be on the screen. We create a command string from the values of those sliders and the angle of our joints. And then periodically, in this case every 50 milliseconds, I'm going to write that command string to the hardware.
So I've just powered up the robot and you may hear a faint buzzing noise in the background. That's the servos. And I'm now going to run the application that we've just created. And we can see it's sort of jolted into position. That's okay, that's all of our slider values being centralized. So I'm going to start at the top with the claw. So I can move the slider and I get an instant response from the claw. The next joint down rotates the claw. The joint after that is like a wrist joint, so that can move the claw backwards and forwards. The joint after that is like an elbow joint, and the joint at the bottom is a shoulder joint. To make sure this stays in the video feed, I think it's okay. The shoulder joint, and the final servo is sort of a shoulder rotation joint. So I'll overlay the sliders with the actual application, but what I think we can see is it's a very responsive system. So that's sliders from an external Pixel Game Engine extension library, opening a COM port, talking through virtual COM port via Bluetooth. The Bluetooth is talking via UART to the embed controller. The embed controller is running C++ code to set the PWM values for the servo motors, and the servo motors are actuating the individual parts of the robot. I'll just try and position that down. Oop, wave it around a bit. As you can see, driving the robot is not as simple as it should be. We'll also notice the robot is wobbling all over the place and it's quite jerky. Mainly that's because it is quite a cheap robot, but secondly, we have no trapezoidal acceleration curves, and that might be the topic of the next video in this series, is how do we actually create proper smooth motion curves rather than just slamming PWM values around. Quite an important thing to do when working with robotic systems. So, if you've enjoyed this video, a big thumbs up please, and have a think about subscribing. Of course, I'll put all of the source code on the GitHub and link to it below. I'll also put the embed source code as part of the Pixel Game Engine file we've just created on the GitHub too. A big thanks again to all of the Patreons that have made this particular project possible. I've had lots of fun with it. And so I think for this video, that's it. Take care, and I'll see you next time.